So if you still remember, we have a beam in bending, alright, and then there are experience a certain compressive over here and a certain tensile stress over here, alright. For elastic region, we can actually model this thing as over here, right? There's the arrows all over here. This is for this portion only, alright. And if you have something going in this direction, alright, then it's talking about this thing, right? It should be the same size, right? Some sort of like that, alright? It's moving in this direction, okay? Now, if you continue to bend, the compressive over here and the tensile stress over here will increase, alright? So right at that point over here, when this point start to reach its yield strength, alright, the rest will follow. So somewhat the outcome will be something like this, okay? So this, when the material can't flow anymore, you'll somewhat, maybe I should have a different, instead of going straight anymore, it will just go like this, alright, it will start to crumple, and the rest of this still linear, alright, the rest of this still somewhat corresponding over here, and this part will crumple because you have nowhere to go, because you're talking about another small analysis, alright, talking about another piece, so to speak, alright, or maybe I should have drawn in. So we have another piece over here, alright, and therefore this another piece over here will also experience this particular phenomenon, alright, the rest straight line, so on and so forth, alright. We also make known to you that when this thing starts to occur, alright, you may have a bump over here, alright, so normally we will see some bump, and then over here you may see some tearing, alright, due to the tensile pulling of this part. So as you can see, you will someone pull it off, alright, these are the stuff. If you were to bend it furthermore, alright, you'll see something like this, alright, this is the compressive, this is the pulling, alright, and things like that. So for this case, going here is this one, alright, it's this two, and you'll have another side over here like this. So this part is somewhat being stretched still, alright, but at least you can see some of the stress point. Explain that why when the more you bend, the material itself will start to flow, and nowhere to flow, it will actually stuck here and create a bigger bump, right? Create a bigger bump, and you will somewhat start to crack, and things like that happens. Therefore, based on what we have seen just now, show that for a beam subjected to a pure bending yielding will initiate a certain moment, when a moment initiated was this, alright, and the plastic collapse will not occur until this happens. So these are the moments, but how do we derive these moments? Alright, how do we derive? And therefore let's go. For a shape like this, alright, this is very nice. This is not considered yielding. There is no yielding in there. It's just simply elastic because of this line over here. Alright, then if you were to continue to bend it more over here, alright, you can see that instead of this thing over here right now, alright, it start to become like this, correct? Maybe, yeah, something like this. So somewhat the material actually flow and somewhat stuck over here, and you get what I mean. And the more you bend and up till all the materials are yielded, then this thing happens, and you're gonna somewhat cause a fracture or cracks happens, alright. But let's take a look into this situation, because we are actually keen to see that the material itself is due to a pure bending yielding, alright. So we want to see something that is yielding, and therefore we'll talk about something that yields but not fully yield until it cracks, like this case, alright. So we want to see something that really yields, alright. So when you're talking about moments, let's set this thing over here as plus, while this direction over here is minus, okay. So far, because we are talking about moments, and we know that moment, I'll just zoom it out, alright. We know that the moment is the force times the perpendicular distance, alright. How do we set a force, and how do we set the perpendicular distance? And therefore, let's start. We start first by talking about the force. We know that the force is stress times area, okay. So how do we, in terms of this, how do we look at the stress, and how do we look at the area? So for such a case, I'll look in terms of a slightly exaggerated, grossly type of stuff. So what do I mean? So this piece over here, alright, is similar to this one. But however, later on you'll know what I mean, that this one can represent any of the little cubes over here. So each of the cubes has this shape over here. Alright, so anyway, let's go to 3D first. Wrong shape. Alright, what do I mean? Okay, I'm actually interested in looking at this point. Alright, so in symmetry, by symmetry, alright, this point over here, this thing over here is the same as this, right? It's totally the same. Both of them are the same. Alright, and with a certain neutral axis. Alright, so therefore I'll just take this shape rather than this shape. Later on you'll know why, because it's easier for me to do. Alright, so this is it. If I were to flip this horizontally, then I have this shape over here. Right, it's the same thing over here at this particular point. So it depends on how and they are in fact the same stuff. Alright, and therefore if we were to go to 3D now, someone see this phenomenon. Alright, your stresses are all acting over here. Alright, and these are all the linear one. Mark the blue color as the one that actually starts to yield and create this boundary over here. Alright, while the green color are still yielding. Alright, this applies to all the cross-sectional over here. Alright, this applies to all the cross-sectional over here with all this linear stuff. Alright, and if you were to go to 3D now, alright, this thing over here, right here, can be re-represented as a small cube in a beam, like this. So this particular cube over here, alright, maybe I should draw something like this, alright, is somewhat, we call this the dA, alright, certain area. Alright, maybe I should just crop this one over here, that's all. This is the dA I'm talking about. Alright, now since I'm already here, why not I just draw a few other cubes, alright, other small cubes that I can show you more things, right? Here, alright, and we have their own stresses that is acting all over the side. Alright, and the linear, if you were to zoom in, this pathway all along this stretch of the beam. Alright, for example. Okay? And just below of them is another set of system. Alright, but however, at this particular point over here, this top point and this top point experience more stresses than your bottom one. Alright, therefore the bottom one didn't actually become like this. Right, it didn't actually bend, right? So it's just a straight linear system still. Alright, so it is pretty nice. Alright, it's pretty nice. It's going in this manner, and this is going in this manner. Alright, so somewhat it is still safe. After a certain point it may actually become like this. Okay? But I haven't yet. Alright? So just to show you that different points of the beam will experience different stresses and different yielding, yeah, correct. And therefore let's just talk about some dA. Alright, just take a cube over here and just pluck it out. Alright, this is some dA. Alright, this is some dA. And then this dA has a particular force. Alright, we call this the stress. Alright, the stress multiplied by its area will give you your force. So far so good. And let's just plug it in. Alright, but however, you just need to know that we're talking somewhat of this portion, this shape. So if I have to draw it out again, 2D is like this. In 3D now, it's something like this. Alright, you can actually see a clear portion that this part over here, this shaded part over here, is still linear. Alright, it's still somewhat very nice. It didn't actually yield, so it's still pulling in this straight direction. However, at this portion over here, you'll start to have a plastic flow. Alright, you'll start to flow in manners that causes a certain bump. Right, if you were to show you over here, alright, if at this particular point, alright, you may have certain bump, alright, over here. So you somewhat causes the beam to actually bend in such manner. And at the bottom, maybe it has some sort of a this type of cracks over here. Alright, this plasticity deforms. Deformations, I would say. Stresses over here has nowhere to go but just boom up and just create a bump over here because it has no more space to go. Alright, things like that. Okay, simply color this piece over here, this this somewhat the yielded part over here as blue color. So I'll just color now. While the elastic region, I'll just color as the orange color one. Okay, if you were to go on all the way, what we'll have is something like this. Okay, then if you were to look in this direction now, you'll see something like this. Okay, wow. If you were to see in this view, you'll see something like this. Alright, so this part over here, somewhat, as you can see, experiences yielding. And therefore this stress over here is the stress is equals to your SY, your yield strength. Because if you remember, if you reaches the yield strength of the material, anything larger than that will start to, any stress larger than your yield strength will start to cause yielding. Alright, and the stuff starts to flow in this manner. Alright, and it can't flow in a straight path anymore. Alright, and likewise for this blue color region over here is going in this direction. Alright, because it's this part over here, if you were to just zoom out a little, this part over here is compressing, and the bottom one is actually pulling. Alright, so there are different ways, and we say that going in this direction is negative. Alright, and therefore we have somewhat the stresses over here already. Alright, you may wonder why I keep talking about why I keep talking to you about these things. Later on you'll know that we will just combine everything together. Alright, and this orange color region, alright, this orange color region over here, alright, these are all your so-called the elastic region. So therefore you can apply your M over I is equals to 1. Alright, since you know that you don't know your M and you have not much information of I, you can just use your E over R is equals to sigma Y. And therefore I have E over R Y is equals to sigma. And since you know that your sigma is equals to SY such that it will start to yield, then we can just equate EY over R equals to SY. And because this line over here, alright, is turning in this manner, alright, it's tilting in this manner, alright. For example, at first it was like this, right? And as you continue to bend the system, this line becomes steeper, and then eventually it will become like this, right? So this line actually goes by an angle all the way up till it reaches your real axis. So it's actually going in this direction. So in somewhat of a sense, it's going in this direction, and therefore we say that this direction is the minus, and therefore I can simply say that this is a minus EY over R, which is also can be rewritten as E over R is equals to minus SY. Alright, so these are all the stresses that acts upon all these colors. Alright, so I'll just rearrange things so that you can easily see things. Hold on a while. And since they are different colors and they are actually somewhat proportional in length, this length is equals to this length. Alright, maybe I should say that it's A over 2 lah. Right, A over 2 over here. Alright, so they are somewhat the same of the length. So I can say that this piece over here is dA, this piece over here is dA, this piece over here is dA, and this piece over here is dA. So there is 4 dAs, alright, in such of a sense. Alright, because we are simply 4 system, alright, because this part over here is this one also. Alright, this whole chunk over here uses this formula. But in terms of the axis, because you have to increase the beam, if I have to show you the beam again, it's the beam right now, and you have a certain neutral axis. Alright, and therefore it cuts them into four sections. This is the first section, this is the second section, this is the third section, and this is the fourth section. Alright, if you can't see properly, it's the second section. Hopefully you see what I mean. So this blue one is the first section, this orange one is the second section, this third one is the third section, the orange color is the third section, and this one is the fourth section. Okay, so far so good. And then we will just bring everything, we'll just look into this direction now, which is the common direction that we often look in, and therefore we have this one. Alright, and if you were to just draw it out all over here again, this is what we have just seen earlier, the 3D form, and you have your certain neutral axis. Alright, if it's bending or if it's not bending, it's something like this. Alright, and therefore if they go into 2D now, alright, this is your stuff right here. And therefore somewhat I'm actually naming this point over here as C, then this point over here as A, and this is the origin 0, and likewise over here instead of A it's minus A, and this point over here is minus C. Alright, as you can see, it's all reflected over at this contour over here, which is what I've done to show you. Alright, just take a look and check it out. Alright, so let's set up the equation. Alright, we know that there will be a forces. Alright, the stresses is equals to your yield strength, right? So if you were to multiply by your particular dA over here, alright, so you have stress times your dA. Alright, so you are multiplying a certain small portion of your area. Alright, this portion over here, if we were to go into 3D now. Alright, so this small portion is your area, this portion is another dA, as we say, and however this is the orange color one, so therefore it's talking about the EY over R multiplied by your dA, and this is also minus EY over R over your dA. Alright, and this thing over here is the forces, is the stress times your dA. Alright, and this stress is your if you were to remember, this stress is your yield strength, right? Because this square over here tells you that you are actually your material has been yielded. Alright, since you see the square, you know that the material has been yielded, and therefore it's definitely, the stress is definitely a yield strength. Same as this thing, can simply write as the yield strength. Alright, so I'm taking the integral between all of these little squares. So what I have is something like this. Alright, from minus C to minus A, from minus C to minus A, this dA, this SY dA is our forces. Alright, as we have shown over here, SY times dA. Alright, should be here lah, because we're talking about this range. Alright, so it's SY times dA. So far so good. And then plus from A to C, which is talking about this thing. Alright, because this is, if you were to remember, just check it out. This one is A, this is C. Alright, so I'm talking about this portion over here right now. Okay, so I'll just retake off. So this is from A to C, and talking about SY dA also, this is the forces. Okay, and you may wonder what is this Y, because you are talking about moment is force times perpendicular distance. So this Y distance is all the way extend, alright, all the way extends to the middle of your neutral axis of your beam. Alright, this is the distance Y. Alright, if you were to take a look in terms of 3D, hold on. Our small area here is actually this portion over here. Alright, these are all the dAs. The dAs over here. Alright, and the distance from your neutral axis. So it's from here to Y. Alright, somewhat. Alright, so this is the distance from your neutral axis. Alright, and just to let you know that the explanation for my dA over here may be somewhat a bit discrepancies, may be wrong. Alright, but it's in terms of the dA itself. Alright, so therefore it's still somewhat legit in the equation, but just let you know that my explanation may be wrong. Alright, and the Y itself therefore is this perpendicular distance. Alright, because your force is acting to this direction, which is your stress times your area, or your dA, and then this is somewhat your yield strength times your dA. Alright, and the perpendicular distance is your Y. Okay, so this is why I'm setting up this equation. As for 0 to A, or minus A to 0, this is the elastic region. Alright, and that elastic region we know that is EY over R. So I'll just simply sub in as EY over R first. Alright, and the EY over R is for the 0 to A region. Alright, same thing is dA times Y, which is your perpendicular, your area times your particular Y. So from this understanding, I would see that this whole piece is dA. Alright, instead of the one that I've I've sectionize all the stuff over here. We say that this is dA, this piece is dA, this is another dA, this is another. No, it shouldn't be. Alright. So we have just finished setting up the equation for all the 4 terms of your stress state. Alright, your beam bending moment stress state. So in the next video, hopefully we can derive what the question wants us to do. If you still remember, we are dealing with a question, alright, because we are dealing with the pure bending yielding, alright, the moment. Alright, so we're going to derive this equation and then eventually derive something else. Okay, I shall see you in the next video.